Hello everyone and welcome to my presentation on FlowPy. What is FlowPy? FlowPy is a model that identifies process areas of gravitational hazards, such as avalanches, rockfalls or soil slides. Due to the simplicity of this model, we can cover simulation areas on a regional scale. On the right side you see the digital elevation model of our test area, overlaid with the model results. The colors indicate the kinetic energy, increasing from dark purple to bright yellow colors. You can see how the kinetic energy generally increases from the starting areas to the middle of the track and then abruptly decrease in the runout areas. We got a lot of inspiration from former models like FlowR and GPP. Let's talk about the model. The model is written in Python to keep it easy adjustable. The runout routine of FlowPy is based on the principles of energy conservation, including frictional dissipation assuming simple Coulomb friction, leading to a constant travel angle. Potential release areas and the corresponding travel angle have to be adapted for each type of gravitational mass movements. An important improvement compared to similar models is that it can handle mass movement in flat and uphill terrain. We achieved this by adapting the algorithm of Holmgren from 1994. The Holmgren algorithm works only in a range from 0 to 90 degrees. To achieve a flat or uphill flow, we had to change this from -90 to 90 degrees. The persistence function calculates in which direction a process will spread, regarding the direction in the former calculation step. This is a simple method to bring conservation of momentum in the model. In comparison to other models, we scale the direction cosines with the amount of energy coming from the input cells. This means an input with higher energy will have a higher influence in where the process will flow. In the last step, we multiply the calculated values for flow direction and persistence and normalize them. By multiplying it with the previously determined susceptibility of the center cell, we get the susceptibilities for the neighbor cells. If the result is lower than a threshold value, there will be no spreading in this direction. Let's have a look on our example now. To show some results, we chose an area in Austria on the border to Italy. The minimum altitude in this area is around 1100 meters and the maximum at 3400. The area covers a region of 200 square kilometers and around 50 avalanche paths. The animation we see here shows us the runout zones from avalanches, including the maximum possible velocity, where bright is fast and dark is slow. This information is not needed if we want to identify protection forest, but in a future step we want to identify the forest effect against avalanches, and therefore we want to compare the velocities with and without forest, or from different types of forest. But let's go on with the identification of protection forest. In the next animation, we see the infrastructure layer that is needed for the identification of protection forest. It includes ski slopes, streets, highways and buildings. Forest roads are not taken into account because they would increase the area of protection forest to an unusable value. How do we identify protection forest? Every time an avalanche hits infrastructure, we calculate the way back to the release pixel and save this as a so-called back calculation. This back calculation includes then the release and the runout to the infrastructure. By overlaying the forest cover with the back calculation, we can identify which forest area has a protective function. With these results, FlowPy is a tool that can be used to identify forest areas that are important for hazard protection.